Welcome to Fall Asleep channel. Tonight, how the Earth continuously reshapes itself through plate tectonics, the rock cycle, erosion, and deep internal heat over geological time. Now allow yourself to get comfortable and enjoy quiet and pleasant rest. Let's begin. Geology begins not with motion that can be seen, but with structure that exists beneath the surface. The outermost layer of the Earth is called the crust. It is thin in comparison to the layers below. Under oceans, it may be only a few kilometers thick. Beneath continents, it extends deeper, composed mostly of silicate minerals rich in oxygen and silicon. This crust rests upon the mantle, a vast layer of solid rock that behaves over long spans of time as a very slow-moving material. Not liquid in the ordinary sense, but capable of gradual flow under heat and pressure. Temperature increases with depth because heat remains from the planet's formation and continues to be generated through radioactive decay of elements such as uranium, thorium, and potassium. This internal heat drives convection within the mantle. Convection occurs when warmer material becomes slightly less dense and rises, while cooler material sinks. The movement is measured in centimeters per year. Yet over millions of years, it reshapes the surface entirely. The crust and the uppermost portion of the mantle together form the lithosphere. This rigid outer shell is not continuous. It is divided into tectonic plates. Each plate moves slowly relative to the others, driven by forces associated with mantle convection, slab pull, and ridge push. Where plates move apart, magma rises from below, cools, and forms new crust. This process occurs along mid-ocean ridges, creating long underwater mountain chains. The newly formed rock records magnetic signatures aligned with Earth's magnetic field at the time of cooling, preserving a timeline of seafloor spreading. Where plates move toward one another, different interactions occur depending on their composition. When oceanic crust meets continental crust, the denser oceanic plate subducts beneath the lighter continental plate, descending into the mantle. As it sinks, it releases water trapped within minerals, lowering the melting point of surrounding mantle rock. This produces magma, which rises and may form volcanic arcs along continental margins. These volcanoes are surface expressions of deeper processes driven by density contrast and heat transfer. When two continental plates collide, neither easily subducts. Both are buoyant relative to the mantle. Instead, they compress and thicken. Rock layers fold and fault, forming mountain ranges through uplift. The Himalayas continue to rise as the Indian plate presses into the Eurasian plate, though uplift is balanced by erosion acting simultaneously at the surface. Erosion is the gradual removal and transport of material by wind, water, ice, and gravity. Rainfall breaks down exposed rock chemically and mechanically. Rivers carry sediment toward lower elevations. Glaciers carve valleys through persistent movement of ice over bedrock. Each grain of sediment represents rock that has been weathered, detached, transported, and eventually deposited elsewhere. Sedimentary basins accumulate these particles in layers. Over time, pressure compacts them, and minerals precipitate between grains, forming sedimentary rock. Igneous rocks originate from molten material. When magma cools slowly beneath the surface, large crystals form, producing coarse-grained textures such as granite. When lava cools rapidly at the surface, crystals remain small, forming basalt or obsidian. Metamorphic rocks develop when existing rocks are subjected to heat and pressure without fully melting. Minerals recrystallize, aligning into new structures that reflect conditions at depth. These processes connect through the rock cycle. Any rock type may transform into another given sufficient time and changing conditions. Igneous rock may weather into sediment. Sediment may lithify into sedimentary rock. Sedimentary rock may be buried and metamorphosed. Metamorphic rock may melt and become magma. The cycle does not follow a fixed sequence. It responds to environmental forces and tectonic movement. Earthquakes occur when accumulated stress along faults exceeds the strength of rock. Plates do not move smoothly at all boundaries. Friction locks sections together. Strain builds gradually, and when released energy travels outward as seismic waves. These waves propagate through the Earth, revealing information about internal structure through their speed and refraction. The planet's core lies beneath the mantle, composed primarily of iron and nickel. The outer core remains liquid due to high temperature, while the inner core is solid because immense pressure prevents melting despite even higher heat. Motion within the liquid outer core generates Earth's magnetic field through the geodynamo process. This magnetic field shields the surface from charged particles originating from the sun. Over geological timescales, continents shift position, oceans open and close, mountain ranges rise and erode. Climates change as land masses alter atmospheric and oceanic circulation, yet each transformation arises from measurable forces: heat transfer, gravity, pressure, chemical reaction, and the slow movement of solid rock responding to those forces. Geology therefore observes a planet that appears stable on human timescales, yet continuously adjusts over millions of years. Mountains are not fixed structures. They rise, erode, and eventually return as sediment to the sea. Ocean floors are not permanent. They form at ridges and are recycled into the mantle at subduction zones. The surface visible today represents a temporary arrangement within a system driven by internal heat and external weathering. Beneath quiet landscapes, mantle convection continues. Plates shift by small increments. Minerals crystallize under pressure. Sediments accumulate grain by grain. And the lithosphere responds slowly to forces that operate without pause. In this gradual and ongoing motion, the solid Earth remains dynamic, balanced between heat from within and erosion from above, shaped not by sudden design, but by continuous physical processes unfolding across deep time. Deep beneath the lithosphere mantle, convection continues in patterns that are neither chaotic nor hurried, but governed by viscosity and thermal gradients. The mantle is solid rock, yet at temperatures exceeding 1,000 degrees Celsius and under immense pressure, it deforms plastically over geological time. Crystals within mantle minerals shift along microscopic defects, allowing the material to flow slowly without melting. This slow circulation transfers heat upward from the deeper interior toward the crust, maintaining the energy that drives plate motion. As oceanic lithosphere moves away from mid-ocean ridges, it cools and becomes denser. Cooling increases thickness because newly formed crust and upper mantle contract as temperature declines. Eventually, this aging lithosphere may become dense enough to sink when it encounters a subduction zone. Slab pull arises from the gravitational force acting on this descending plate, drawing the remainder of the plate behind it. This force is considered one of the primary drivers of plate tectonics. Within subduction zones, sediments carried on the oceanic plate are scraped off and accreted onto the edge of the overriding plate, forming accretionary prisms composed of folded and faulted sediment layers. Deeper portions of the subducting slab release fluids that rise into the overlying mantle wedge, lowering its melting point. Partial melting generates magma with chemical signatures distinct from mid-ocean ridge basalt, reflecting contributions from both mantle material and altered oceanic crust. Magma rising through continental crust may stall and crystallize slowly at depth, forming plutonic bodies that later become exposed through uplift and erosion. Batholiths, such as those found in the Sierra Nevada, represent ancient magma chambers now visible at the surface after millions of years of overlying rock removal. The rate of erosion determines how quickly such deep structures emerge. Rivers insize downward as land is uplifted, maintaining dynamic equilibrium between tectonic uplift and surface denudation. Fault systems accommodate motion between plates and within them. Transform boundaries allow plates to slide horizontally past one another. Shear stress accumulates along these faults until rupture occurs, releasing energy as seismic waves. Primary waves travel through both solid and liquid materials. Secondary waves propagate only through solids. Analysis of their behavior reveals that Earth's outer core must be liquid because secondary waves do not pass through it. The distribution of earthquakes outlines plate boundaries globally. Shallow earthquakes occur along divergent and transform margins. Deeper earthquakes trace descending slabs within subduction zones, some reaching depths of several hundred kilometers, indicating that the subducted lithosphere retains rigidity even as it penetrates the mantle. Volcanic activity varies according to tectonic setting. At mid-ocean ridges, basaltic magma erupts gently due to lower viscosity and gas content. At subduction-related volcanoes, magma often contains higher silica content, increasing viscosity, trapping gases, and producing more explosive eruptions when pressure is released. Pyroclastic material may blanket surrounding landscapes, later consolidating into volcanic tuff. The chemical composition of rocks provides insight into their origin. Igneous rocks crystallize from melt and preserve mineral assemblages that reflect cooling history and source material. Sedimentary rocks preserve evidence of depositional environment through grain size, sorting, and fossil content. Metamorphic rocks record temperature and pressure conditions through index minerals that form only within specific ranges. The rock cycle operates continuously but unevenly across regions. Uplifted terrains expose fresh rock to weathering, while subsiding basins accumulate sediment. Chemical weathering alters feldspar minerals into clay through hydrolysis reactions involving water and carbon dioxide. Physical weathering fractures rock through freeze-thaw cycles, thermal expansion, and biological activity. Roots exploit cracks, widening them gradually. Sediment transported to the ocean may settle in layers that preserve a chronological record, each stratum reflecting conditions at the time of deposition. Fossils embedded within these layers document biological evolution and environmental change. Radiometric dating of minerals containing radioactive isotopes allows determination of absolute age. Uranium decays to lead at a known rate. providing a clock embedded within crystalline structures. Isostasy describes the gravitational balance between lithosphere and underlying mantle. Thick continental crust floats higher because it is less dense, much like ice floating on water. When erosion removes mass from mountain ranges, the crust responds by rising gradually, maintaining equilibrium. Similarly, when sediment accumulates in basins, the added weight causes subsidence. Over hundreds of millions of years, continents assemble into supercontinents and later fragment. Plate motion reorganizes ocean basins and alters climate through changes in ocean circulation and atmospheric patterns. The breakup of Pangaea reshaped coastlines and redistributed ecosystems, influencing evolutionary pathways across geological epochs. Deep time extends beyond human perception. Processes measured in millimeters per year accumulate into mountain belts thousands of meters high. Sediment grains deposited slowly over ages form rock sequences kilometers thick. Magnetic minerals align with Earth's field and record reversals that occur irregularly through time, providing markers within the geologic record. Beneath every landscape, mantle convection continues without pause. Heat flows outward, plates shift, rocks deform, minerals recrystallize, and sediments settle. The solid Earth appears motionless across a lifetime. Yet on the scale of millions of years, it is dynamic and responsive, governed by thermodynamics, gravity, and chemical transformation, in continuous adjustment between internal energy and surface processes shaping the evolving planet. As geological time extends further, the processes that shape the surface become intertwined with cycles operating within the atmosphere and oceans. Carbon moves between rock, water, air, and living systems through the long carbon cycle. Volcanic eruptions release carbon dioxide stored within the mantle into the atmosphere. Rainfall dissolves carbon dioxide into weak carbonic acid, which reacts with silicate minerals during chemical weathering. These reactions transport dissolved ions to the oceans where they precipitate as carbonate minerals, forming limestone. When such carbonate rocks are later subducted, some carbon returns to the mantle, completing a cycle measured in millions of years. This exchange regulates atmospheric carbon dioxide over deep time and influences global climate stability. The formation of continental crust differs from oceanic crust in both composition and longevity. Oceanic crust forms continuously at spreading centers and is recycled within roughly 200 million years. Continental crust, being less dense and more buoyant, persists far longer. Some continental cores, known as cratons, contain rocks more than 3 billion years old. These ancient regions represent stabilized lithosphere that has resisted recycling through tectonic processes. Minerals crystallize according to temperature and pressure conditions described by phase diagrams. Olivine forms at higher temperatures in mafic magmas. Quartz crystallizes at lower temperatures in silica-rich systems. During metamorphism, certain minerals transform into new structures stable under increased pressure. For example, graphite may transform into diamond at depths exceeding 100 kilometers, where pressure alters atomic bonding. Yet even diamonds may eventually return toward the surface through volcanic processes such as kimberlite eruptions. Groundwater circulates through pore spaces and fractures in rock, dissolving and redepositing minerals as it moves. Over long periods, this circulation can create extensive cave systems in soluble rocks like limestone. Stalactites and stalagmites grow from gradual precipitation of calcium carbonate as water drips and releases dissolved carbon dioxide, each layer forming slowly, recording subtle variations in climate within its chemical composition. Plate tectonics also influences the distribution of natural resources. Hydrothermal fluids associated with magma bodies transport dissolved metals through fractures. As temperature and pressure conditions change, these metals precipitate to form ore deposits. Gold, copper, and other elements accumulate in concentrated zones due to these processes, demonstrating how internal heat drives both structural change and mineral distribution. The magnetic field generated within the liquid outer core not only shields the planet from solar wind, but also leaves a record within cooling igneous rocks. When lava solidifies, iron-bearing minerals align with the prevailing magnetic field, preserving its orientation. Reversals in magnetic polarity are captured symmetrically along mid-ocean ridges, confirming the mechanism of seafloor spreading. This paleomagnetic evidence provides quantitative support for plate tectonic theory. Sea level fluctuates across geological time due to changes in global ice volume and the configuration of ocean basins. When mid-ocean ridges are more active and elevated, they displace seawater, raising global sea level. During glacial periods, water stored in continental ice sheets lowers sea level, exposing coastal plains. These fluctuations leave sedimentary records in shoreline deposits and marine fossils found inland. Impact events from extraterrestrial bodies have also influenced geological history. Large meteorite impacts release immense energy, excavating craters and altering climate through atmospheric dust injection. The boundary marking the end of the Cretaceous period contains elevated iridium levels, evidence of such an impact, demonstrating that external forces occasionally intersect with internal processes to shape planetary evolution. The thermal evolution of the planet proceeds gradually as internal heat dissipates. Radioactive decay continues to generate heat, but at diminishing rates over billions of years. Mantle convection patterns may shift as heat flow decreases, influencing tectonic activity in the distant future. Yet at present, sufficient heat remains to sustain plate motion and volcanic activity. Rocks exposed at the surface are continuously recycled through weathering, transport, burial, and metamorphism. Even the highest mountain peaks consist of material once buried deep beneath earlier landscapes. Uplift brings ancient rocks into view while erosion lowers once prominent features. This balance between uplift and denudation maintains dynamic topography over time. Geology therefore observes a planet governed by interconnected cycles. Thermal convection within the mantle drives plate movement. Plate movement creates mountains and ocean basins. Erosion redistributes material across the surface. Chemical reactions alter mineral structures. Sediments accumulate and lithify, and deep burial initiates metamorphism or melting. These processes proceed at rates slow enough to seem imperceptible. Yet over millions of years, they reshape continents and oceans entirely. Beneath forests, deserts, mountains, and seas, the lithosphere remains in motion, responding to internal heat and gravitational equilibrium. Above it, weathering and climate continue to modify exposed surfaces. The solid Earth exists not as a static foundation, but as a dynamic system, adjusting gradually, continuously, and without pause across spans of time far exceeding human experience, steady in its processes, measured in its transformations, and sustained by the persistent flow of energy from its interior toward the surface. As time extends further into geological perspective, the record of these processes becomes layered within the rocks themselves. Stratigraphy examines the order and relative position of sedimentary layers. Younger strata typically overlie older ones unless later deformation has altered their arrangement. Folding and faulting may tilt or invert sequences. Yet careful observation of cross-cutting relationships allows reconstruction of the sequence of events. An igneous intrusion that cuts through sedimentary layers must be younger than the layers it penetrates. A fault displacing rock units must be younger than the rocks it offsets. Through such relationships, the chronology of landscapes can be deciphered without direct measurement of age. Radiometric dating refines this timeline by quantifying the decay of unstable isotopes within minerals. When zircon crystals form within cooling magma, they incorporate uranium atoms into their structure but exclude lead. Over time, uranium decays into lead at a predictable rate. By measuring the ratio of parent-to-daughter isotopes, the crystallization age of the mineral can be determined. These methods reveal that the Earth formed approximately 4.5 billion years ago, establishing the framework within which all geological processes operate. The early Earth differed significantly from present conditions. Intense volcanic outgassing released water vapor and gases that condensed to form early oceans. Heavy meteorite bombardment shaped the young crust. As the surface cooled, stable continental fragments began to form. The development of plate tectonics likely transformed heat distribution and surface morphology, enabling recycling of crust and influencing atmospheric composition through long-term carbon cycling. Fossils preserved within sedimentary rock document the progression of life through time. Trilobites appear in early Paleozoic strata. Dinosaurs dominate Mesozoic layers. Mammals diversify in Cenozoic deposits. Extinction events mark boundaries where rapid environmental change altered ecosystems globally. These biological transitions are recorded alongside volcanic ash layers, impact debris, and climate indicators, integrating biological evolution with geological context. Glaciations leave distinct signatures within the rock record, striations carved into bedrock by moving ice, unsorted glacial till deposited directly by melting glaciers, and drop stones embedded within fine marine sediments indicate periods when ice sheets extended across continents. Oxygen isotope ratios within marine fossils reveal fluctuations in global ice volume and temperature, allowing reconstruction of paleoclimate over hundreds of thousands of years. The movement of continents alters ocean circulation patterns, influencing heat distribution and climate. When continents cluster near the poles, ice sheets may expand, increasing albedo and reinforcing cooling. When continents occupy equatorial regions, chemical weathering rates increase under warm, wet conditions, drawing down atmospheric carbon dioxide and gradually moderating temperature. Thus, tectonics and climate remain interlinked through feedback mechanisms operating over millions of years. Earth's interior continues to cool slowly as heat escapes toward the surface. Conductive heat transfer through the crust operates continuously, though at much slower rates than convective transport within the mantle. Hotspots represent localized upwellings of hotter mantle material, forming volcanic island chains as plates move over them. The Hawaiian Islands record sequential formation as the Pacific Plate passes above a stationary mantle plume, each island marking a point where magma once reached the surface. Mineral stability fields shift with depth. Increasing pressure transforms familiar surface minerals into denser polymorphs within the mantle. Olivine transitions into wadsleyite and ringwoodite at specific pressure ranges. These phase changes influence seismic wave velocities, creating detectable discontinuities that define boundaries within the mantle. Seismic tomography uses variations in wave speed to image subsurface structures, revealing subducted slabs and mantle plumes extending thousands of kilometers beneath the surface. Even the slow rebound of land following glacial retreat reflects geological equilibrium. When massive ice sheets melt, the removal of weight allows the lithosphere to rise gradually in response to isostatic adjustment. Regions once depressed beneath kilometers of ice continue to uplift thousands of years after glaciation ends, demonstrating the long memory of solid Earth response to surface loading. Through every transformation, the governing principles remain rooted in physics and chemistry. Heat flows from hotter regions to cooler ones. Pressure increases with depth. Density determines buoyancy. Minerals crystallize according to thermodynamic stability. Erosion lowers relief while tectonics raises it. The visible landscape at any moment represents a transient configuration within ongoing cycles of uplift and denudation. Geology, therefore, studies a planet that evolves continuously yet predictably within natural laws. Mountains rise through collision and are reduced by weathering. Ocean basins open and close through spreading and subduction. Rocks melt, crystallize, fracture, and metamorphose. Elements cycle between interior and surface reservoirs, and time integrates these incremental processes into profound transformation. Beneath the quiet surface of present landscapes, the mantle convects, plates migrate, and minerals adjust their structures in response to pressure and heat, sustaining the slow, measured, and enduring evolution of the solid Earth. As geological processes continue across immense spans of time, the interaction between the solid Earth and the hydrosphere deepens the transformation of surface and subsurface environments. Rivers carve valleys not only through mechanical erosion but also by establishing base levels that control the gradient of tributaries. When tectonic uplift raises terrain, rivers respond by incising downward, maintaining equilibrium between uplift and erosion. Terraces preserved along valley walls mark former floodplain levels, recording pulses of uplift or climatic change that altered discharge and sediment load. Sediment transported by rivers enters deltas where velocity decreases and deposition dominates. The shape of a delta reflects the balance between river input, wave action, and tidal energy. Over time, compaction of accumulating sediment expels pore water and reduces volume, causing subsidence that may be offset by continued sediment supply. If sediment influx declines, subsidence can lead to shoreline retreat, illustrating how geological and hydrological processes operate in tandem. Chemical weathering proceeds through reactions that alter primary minerals into secondary products stable at surface conditions. Feldspar weathers into clay minerals through interaction with water and dissolved carbon dioxide. Iron-bearing minerals oxidize when exposed to oxygen, forming iron oxides that impart reddish coloration to soils and sedimentary rocks. These reactions not only reshape mineralogy, but also influence soil fertility and landscape color. Karst topography develops where soluble rocks, such as limestone, undergo dissolution by slightly acidic groundwater. Fractures widen gradually into conduits. Conduits merge into caverns, and surface depressions known as sinkholes form where roofs collapse. This process illustrates how chemical equilibrium between water and rock drives structural change without dramatic force, only persistence over time. In arid regions, physical weathering may dominate. Temperature fluctuations between day and night induce expansion and contraction within rock, generating stress that fractures surfaces. Salt crystallization within pore spaces exerts pressure that widens cracks. Wind transports fine particles that abrade exposed surfaces, shaping yardangs and desert pavements through continuous yet subtle abrasion. Sedimentary structures such as cross-bedding record the direction of ancient currents. Ripple marks preserve the oscillatory motion of shallow water. Mud cracks indicate drying conditions following deposition. These features encode environmental information within rock, allowing reconstruction of landscapes long vanished. Deep burial of sediment increases temperature and pressure, initiating diagenesis, the gradual transformation of loose sediment into solid rock through compaction and cementation. Pore spaces reduce as grains press together. Minerals precipitate from circulating fluids and bind grains into coherent masses. At greater depths, metamorphism may overprint original textures, recrystallizing minerals into new configurations aligned perpendicular to compressive stress, producing foliated structures such as schist or gneiss. Subduction not only recycles oceanic crust but also transports water and volatiles into the mantle. These components influence melting behavior and contribute to mantle heterogeneity. Some subducted material may remain isolated for extended periods before returning to the surface through mantle plumes. Geochemical signatures in basaltic lavas reveal traces of recycled crust embedded within the mantle's convective flow. The distribution of heat flow across the planet is uneven, highest near spreading centers where new lithosphere forms, lower across stable continental interiors. Geothermal gradients vary accordingly, influencing the depth at which rocks begin to partially melt. Geothermal energy accessible at shallow depths in certain regions reflects localized anomalies in heat transfer. Tectonic stresses accumulate gradually within the crust due to plate interactions. Rocks respond elastically up to a threshold, beyond which brittle failure occurs. The elastic rebound theory describes how deformation builds silently along locked faults until rupture releases stored energy. After displacement, the cycle begins again as plates continue their slow motion. Over geological epochs, supercontinents assemble and fragment repeatedly. Cycles such as the Wilson cycle describe the opening and closing of ocean basins through rifting, seafloor spreading, and eventual subduction. Each cycle reorganizes coastlines, climate patterns, and biodiversity distribution, leaving traces within the stratigraphic and paleomagnetic record. Even the composition of the atmosphere has evolved through geological time. Early volcanic outgassing created an environment with little free oxygen. Photosynthetic organisms gradually increased atmospheric oxygen through biological processes, altering mineral stability and enabling the formation of iron oxide deposits known as banded iron formations. This interplay between geology and biology transformed surface chemistry and influenced subsequent evolution. The lithosphere responds to loading not only from ice and sediment but also from volcanic edifices. Large accumulations of lava add weight to the crust, causing flexure. As volcanic islands grow, the underlying lithosphere bends downward, forming peripheral basins that fill with sediment. When volcanic activity ceases and erosion reduces mass, gradual uplift may follow. Through each of these processes, time integrates small increments into large-scale change. Centimeters of uplift per year produce mountain ranges. Millimeters of sediment accumulation build thick stratigraphic sequences. Fractional degrees of cooling influence mineral transformations at depth. Geology therefore measures continuity rather than abruptness, cycles rather than isolated events. Beneath present landscapes, mantle convection persists. Crustal plates shift incrementally. Rivers transport sediment grain by grain. Minerals adjust to pressure and temperature conditions, and chemical reactions proceed wherever water encounters rock. The surface may appear stable within a human lifespan, yet the Earth remains in motion at scales that unfold across millions of years, governed by gravity, thermodynamics, and the persistent flow of energy from interior to exterior, shaping continents and ocean basins through steady, cumulative transformation. As these transformations continue across deep time, the geometry of the planet's surface adjusts in response to internal and external forces acting together. Continental rifting begins when lithosphere stretches under extensional stress. Thinning reduces pressure at depth and allows partial melting of the mantle. Magma intrudes upward, weakening the crust further. Normal faults develop, creating rift valleys bounded by uplifted shoulders. If extension persists, the crust may eventually split completely. Seawater floods the depression, and a new ocean basin begins to form. The Red Sea represents such an early stage, where divergence continues gradually. The density contrast between oceanic and continental lithosphere ensures that once oceanic crust cools and thickens, it will ultimately return to the mantle at subduction zones. This recycling maintains a relatively constant volume of ocean basins through time, yet the position and shape of those basins shift continuously as plates reorganize. Passive continental margins form where rifting has ceased and tectonic activity subsides. Thick sequences of sediment accumulate along these stable edges, recording long intervals of quiet subsidence. Within continental interiors, stresses may propagate far from plate boundaries, reactivating ancient faults formed during earlier tectonic episodes. These intraplate earthquakes demonstrate that the crust retains structural memory. Zones of weakness inherited from past collisions or rifting remain susceptible to renewed motion when stress fields change. The mantle transition zone between approximately 400 and 700 kilometers depth marks mineral phase transformations that alter density and seismic velocity. Subducted slabs encountering this boundary may stagnate temporarily or penetrate into the lower mantle depending on their temperature and buoyancy. Seismic imaging reveals these deep structures as anomalies in wave speed, offering indirect observation of processes occurring far beyond direct sampling. The lower mantle extends toward the core mantle boundary, where temperatures approach those at the surface of the sun. Though pressure prevents melting in most regions, chemical interactions at this boundary influence heat transfer from the core. Mantle plumes may originate here, rising buoyantly over tens of millions of years until reaching the base of the lithosphere, where decompression melting can generate large igneous provinces. Such provinces record episodes of extensive volcanic outpouring capable of altering atmospheric composition and climate over geological intervals. The core itself remains divided between a liquid outer layer and a solid inner sphere. The crystallization of the inner core releases latent heat and lighter elements into the outer core, sustaining convective motion that powers the geodynamo. Fluctuations in magnetic field intensity and polarity recorded in rocks indicate that the geodynamo evolves over time, yet persists as long as convective energy remains sufficient. At the surface, landscapes respond to variations in climate through feedback with geology. Increased precipitation accelerates chemical weathering. Enhanced weathering can reduce atmospheric carbon dioxide over long timescales, contributing to gradual cooling. Conversely, volcanic emissions may elevate greenhouse gas concentrations, warming the climate until weathering balances the input. This interplay between tectonics, volcanism, and weathering stabilizes climate across millions of years despite shorter-term fluctuations. Sedimentary basins preserve alternating layers reflecting environmental shifts. Transgressions and regressions of the sea leave marine and terrestrial deposits stacked sequentially. Coal layers indicate periods of extensive vegetation in swampy conditions. Evaporate deposits signal restricted basins under arid climates where evaporation exceeded inflow. Each lithologic change represents adjustment to evolving tectonic and climatic conditions. Even subtle tilting of crust influences drainage patterns. Rivers may reverse direction when uplift alters regional slope. Capture events occur when one river erodes headward and intercepts another, reorganizing watershed boundaries. These adjustments reshape landscapes gradually yet decisively over extended periods. The accumulation of strain within continental crust can also lead to ductile deformation at depth. Rocks subjected to high temperature and pressure may fold rather than fracture, forming anticlines and synclines that later become visible when erosion removes overlying material. Such structures reveal that rock at depth behaves plastically over long durations, despite appearing rigid at the surface. Mineral resources form where geological processes concentrate otherwise dispersed elements. Pegmatites crystallizing from late-stage magma may contain rare minerals enriched in lithium or beryllium. Sedimentary processes may concentrate heavy minerals such as gold within river gravels through density sorting. Petroleum accumulates where organic-rich sediments are buried, heated, and trapped beneath impermeable layers, illustrating how organic and inorganic processes intersect within the subsurface. Over billions of years, the cumulative outcome of plate motion has altered continental positions dramatically. Fossils of identical species found on now distant continents confirm that land masses once joined were later separated by seafloor spreading. Paleomagnetic data aligns these reconstructions with precision, demonstrating the mobility of what once seemed immovable. Through every interval, the Earth's structure remains dynamic. Mantle convection transfers heat upward. Lithospheric plates migrate, crust thickens and thins, mountains rise and are reduced, sediments accumulate and lithify, minerals transform under pressure and temperature, and internal energy continues to dissipate outward. The solid Earth does not rush these changes. It adjusts incrementally, continuously, governed by physical laws operating across spans of time far beyond immediate perception. And within this steady progression, geology observes a planet in constant yet measured transformation, balanced between internal heat, surface weathering, gravitational equilibrium, and chemical exchange, unfolding without pause across deep time. As this long continuity extends further, the interaction between tectonics and the oceans continues to refine the surface of the planet in measured sequence. Oceanic circulation is influenced by the geometry of continents, and that geometry is itself determined by plate motion. When gateways between ocean basins open or close, currents reorganize, redistributing heat and nutrients. The closure of the Isthmus of Panama altered global circulation patterns by separating the Pacific and Atlantic Oceans, strengthening certain currents and contributing to climatic shifts in the Northern Hemisphere. This example illustrates how slow tectonic rearrangement can influence atmospheric and oceanic systems far beyond the site of crustal motion. Submarine volcanism constructs vast portions of the planet's surface unseen beneath ocean waters. Pillow basalts form when lava erupts underwater and cools rapidly, creating rounded structures stacked layer upon layer. Hydrothermal vents develop along mid-ocean ridges where seawater circulates through hot crust, dissolving metals and re-emerging as mineral-rich plumes. As the heated water mixes with colder seawater, dissolved minerals precipitate, forming chimney-like structures of sulfide deposits. These processes contribute to ocean chemistry and create localized mineral concentrations. Sediment settling on the deep ocean floor accumulates slowly, often at rates of millimeters per 1,000 years. Microscopic shells of marine organisms composed of calcium carbonate or silica rain downward after organisms die, forming layers of chalk or siliceous ooze. Over time, burial compacts these deposits into rock, preserving microfossils that reveal changes in ocean temperature and chemistry across geological intervals. Continental interiors may experience periods of stability lasting hundreds of millions of years. During such intervals, erosion gradually lowers relief until landscapes approach peneplains, nearly level surfaces representing prolonged equilibrium between uplift and denudation. Yet renewed tectonic forces may later uplift these surfaces, rejuvenating river systems and reinitiating erosion cycles. Rift systems that fail to fully develop into new ocean basins leave behind structural weaknesses known as olicogens. These zones may later influence sedimentation patterns or localize future tectonic activity, demonstrating that incomplete processes still leave lasting structural imprints within the crust. Deep within sedimentary basins, organic material buried under heat and pressure transforms gradually. Biochemical processes convert plant and microbial remains into kerogen. Continued burial increases temperature, breaking complex molecules into hydrocarbons. If permeable pathways and structural traps exist, these fluids migrate and accumulate. The formation of such resources depends on precise alignment of depositional environment, burial history, and structural configuration, all governed by geological timing. Even the slow tilt of tectonic plates influences long-term climate by shifting continents toward or away from polar regions. When large land masses occupy high latitudes, seasonal temperature variation intensifies, facilitating glaciation. Glacial erosion sculpts bedrock and transports vast sediment loads. And when ice retreats, isostatic rebound alters regional elevation, integrating cryospheric processes into the broader geological system. Seismic waves generated by earthquakes continue to refine understanding of Earth's interior. Their reflection and refraction at boundaries reveal layered structure. Velocity variations indicate temperature differences within the mantle, and attenuation patterns suggest partial melt in localized zones. Thus, each seismic event contributes data that illuminates otherwise inaccessible depths. Over immense spans of time, radioactive decay within the mantle gradually decreases as unstable isotopes are consumed. Though the decline is slow, it implies that mantle convection patterns may evolve as internal heat production diminishes. The balance between conductive and convective heat transfer may shift, influencing the vigor of plate tectonics in the distant future. Yet current heat flow remains sufficient to sustain active tectonic cycles. Chemical differentiation early in Earth's history separated dense metallic elements into the core, while lighter silicates formed the mantle and crust. This differentiation established the layered structure that persists today. Gravitational segregation during planetary formation created reservoirs with distinct compositions, and ongoing convection maintains partial mixing within the mantle while preserving overall stratification. The geological timescale divides Earth history into eons, eras, periods, and epochs based on major transitions in rock record and fossil assemblages. These divisions do not interrupt processes but provide reference points for interpreting continuous change. Boundaries mark significant reorganizations of climate, biodiversity, or tectonic configuration, yet the underlying physical mechanisms remain consistent across all intervals. Mountain belts eroded to their roots expose metamorphic cores once buried deep beneath ancient ranges. These exhumed terrains reveal high-pressure minerals indicating conditions far below the surface, demonstrating that crustal material cycles vertically as well as horizontally. Burial and uplift operate in reciprocal phases, shaped by tectonic convergence and erosion. Thus, geology observes a planet that remains internally active and externally responsive. Oceans widen and narrow, continents collide and separate, sediments accumulate and harden, minerals transform under shifting temperature and pressure, and landscapes evolve through uplift balanced by erosion. Every rock surface, every basin, every ridge represents a momentary configuration within a continuum governed by energy flow from the planet's interior and interactions at its surface, steady in motion, cumulative in effect, and enduring across the immeasurable breadth of deep time. As this long continuity extends further, the interaction between tectonics and the oceans continues to refine the surface of the planet in measured sequence. Oceanic circulation is influenced by the geometry of continents, and that geometry is itself determined by plate motion. When gateways between ocean basins open or close currents reorganize, redistributing heat and nutrients, the closure of the Isthmus of Panama altered global circulation patterns by separating the Pacific and Atlantic Oceans. strengthening certain currents and contributing to climatic shifts in the northern hemisphere. This example illustrates how slow tectonic rearrangement can influence atmospheric and oceanic systems far beyond the site of crustal motion. Submarine volcanism constructs vast portions of the planet's surface unseen beneath ocean waters. Pillow basalts form when lava erupts underwater and cools rapidly, creating rounded structures stacked layer upon layer. Hydrothermal vents develop along mid-ocean ridges where seawater circulates through hot crust, dissolving metals and re-emerging as mineral-rich plumes. As the heated water mixes with colder seawater, dissolved minerals precipitate, forming chimney-like structures of sulfide deposits. These processes contribute to ocean chemistry and create localized mineral concentrations. Sediment settling on the deep ocean floor accumulates slowly, often at rates of millimeters per 1,000 years. Microscopic shells of marine organisms composed of calcium carbonate or silica rain downward after organisms die, forming layers of chalk or siliceous ooze. Over time, burial compacts these deposits into rock, preserving microfossils that reveal changes in ocean temperature and chemistry across geological intervals. Continental interiors may experience periods of stability lasting hundreds of millions of years. During such intervals, erosion gradually lowers relief until landscapes approach peneplains, nearly level surfaces representing prolonged equilibrium between uplift and denudation. Yet renewed tectonic forces may later uplift these surfaces, rejuvenating river systems and reinitiating erosion cycles. Rift systems that fail to fully develop into new ocean basins leave behind structural weaknesses known as olicogens. These zones may later influence sedimentation patterns or localize future tectonic activity, demonstrating that incomplete processes still leave lasting structural imprints within the crust. Deep within sedimentary basins, organic material buried under heat and pressure transforms gradually. Biochemical processes convert plant and microbial remains into kerogen. Continued burial increases temperature, breaking complex molecules into hydrocarbons. If permeable pathways and structural traps exist, these fluids migrate and accumulate. The formation of such resources depends on precise alignment of depositional environment, burial history, and structural configuration, all governed by geological timing. Even the slow tilt of tectonic plates influences long-term climate by shifting continents toward or away from polar regions. When large land masses occupy high latitudes, seasonal temperature variation intensifies, facilitating glaciation. Glacial erosion sculpts bedrock and transports vast sediment loads. And when ice retreats, isostatic rebound alters regional elevation, integrating cryospheric processes into the broader geological system. Seismic waves generated by earthquakes continue to refine understanding of Earth's interior. Their reflection and refraction at boundaries reveal layered structure. Velocity variations indicate temperature differences within the mantle, and attenuation patterns suggest partial melt in localized zones. Thus, each seismic event contributes data that illuminates otherwise inaccessible depths. Over immense spans of time, radioactive decay within the mantle gradually decreases as unstable isotopes are consumed, though the decline is slow. It implies that mantle convection patterns may evolve as internal heat production diminishes. The balance between conductive and convective heat transfer may shift. influencing the vigor of plate tectonics in the distant future. Yet current heat flow remains sufficient to sustain active tectonic cycles. Chemical differentiation early in Earth's history separated dense metallic elements into the core, while lighter silicates formed the mantle and crust. This differentiation established the layered structure that persists today. Gravitational segregation during planetary formation created reservoirs with distinct compositions, and ongoing convection maintains partial mixing within the mantle while preserving overall stratification. The geological timescale divides Earth history into eons, eras, periods, and epochs based on major transitions in rock record and fossil assemblages. These divisions do not interrupt processes, but provide reference points for interpreting continuous change. Boundaries mark significant reorganizations of climate, biodiversity, or tectonic configuration. Yet the underlying physical mechanisms remain consistent across all intervals. Mountain belts eroded to their roots expose metamorphic cores once buried deep beneath ancient ranges. These exhumed terrains reveal high-pressure minerals indicating conditions far below the surface, demonstrating that crustal material cycles vertically as well as horizontally. Burial and uplift operate in reciprocal phases, shaped by tectonic convergence and erosion. Thus, geology observes a planet that remains internally active and externally responsive. Oceans widen and narrow, continents collide and separate, sediments accumulate and harden, minerals transform under shifting temperature and pressure, and landscapes evolve through uplift balanced by erosion. Every rock surface, every basin, every ridge represents a momentary configuration within a continuum governed by energy flow from the planet's interior and interactions at its surface, steady in motion, cumulative in effect, and enduring across the immeasurable breadth of deep time. In its final reflection, geology reveals not a sequence of isolated events, but a continuous exchange between interior energy and surface transformation. Heat generated deep within the planet rises slowly through convection, guiding the motion of lithospheric plates. Those plates rearrange continents and ocean basins, and in doing so alter climate patterns, sea levels, and the distribution of life. Mountains rise where crust thickens, yet erosion begins immediately, wearing down relief grain by grain, transporting sediment toward basins where it settles, compacts, and becomes rock once more. The rock cycle does not conclude at any stage. It shifts direction according to temperature, pressure, and position within the crust. Beneath the surface, minerals respond to increasing depth by reorganizing atomic structures. Phase transitions alter density and influence seismic wave speeds. Slabs of oceanic lithosphere descend into the mantle, carrying with them water and sediments that modify melting behavior at depth. Mantle plumes rise where buoyancy allows, delivering heat and magma toward the crust, and volcanic eruptions return material from the interior to the surface, integrating deep and shallow reservoirs into a single dynamic system. Rivers continue to carve landscapes shaped by tectonic uplift. Glaciers expand and retreat in response to climatic variation. Coastlines advance and withdraw with fluctuations in sea level, and groundwater circulates through rock, dissolving, transporting, and redepositing minerals. Chemical weathering moderates atmospheric composition over millions of years. balancing volcanic emissions through silicate reactions that draw carbon into stable mineral forms. The magnetic field generated in the outer core persists as molten iron circulates, recording reversals in rocks that cool at the surface. Seismic waves propagate through the interior whenever stress is released along faults, offering indirect insight into structures far beyond direct observation. Each data set, each mineral grain, each stratigraphic layer contributes to an integrated understanding of a planet in motion. No mountain is permanent, no ocean basin fixed, no continent immovable across deep time. The crust is recycled, reshaped, uplifted, eroded, buried, and renewed. Processes measured in millimeters per year accumulate into transformations spanning thousands of kilometers. What appears solid and unchanging within a lifetime is revealed as fluid and evolving when viewed across millions of years. And so the study of geology rests in continuity, the gradual outward flow of internal heat, the constant adjustment of lithosphere under gravitational balance, the persistent interaction of rock with water and atmosphere, the slow alignment of minerals to pressure and temperature, all unfolding without haste, without pause, governed by thermodynamics and gravity acting across vast intervals. The planet remains active beneath quiet landscapes, steady in its processes, enduring in its cycles, and sustained by the ongoing transfer of energy from its deep interior to its ever-changing surface. If you enjoy peaceful stories like this, you are warmly invited to subscribe and return whenever you need to slow down.